In this episode, we start to explore calculus with a discussion of good and evil. I remember more than 40 years ago, the first day of calculus class, when the professor went to the board to define what it meant for f to be a function. He wrote this on the board, and I looked at that upside down a and I thought, uh-oh. But as he wrote it, he said, for every. And so I wrote that down. After the upside down a, that x epsilon r meant x was in the set of reals. So for every real number x. And then he wrote a backwards e. And he said, there exists. And then he added an exclamation point, which transformed that to there exists a unique. So for every real number x, there exists a unique y that's a real number, and now a backwards epsilon, both Greek and backwards. And he said, such that. So for every real number x, there exists a unique real number y, such that f of x equals y. And that is the definition of a function. We'll come back to functions, and more importantly, we'll come back to the graph of functions, but let's look at curves for a moment. So I have 2 points, let's call them A and B. Let's draw a line from A to B. You may take this literally and use your geometry to draw a straight line, but it doesn't need to be a straight line. When we say draw a line, it can be a curve, something like this. And if you think about how many straight lines go from A to B, well, there's only one, and contrast it with how many not straight lines go from A to B, you get a taste of a recurring theme, which is for most constraints of niceness, in this case, a straight line, more curves are not nice than are nice. There are many more lines between A and B that are not straight than are straight. So there's this one, and there's this one, and there's this one. But this one is a little bit different. It is a line between A and B, but it's not the type of curve we want to consider in calculus. If I draw a vertical line, I can see that this curve is not the graph of a function, because for this x, there are 3 values of y. So this is not the graph of a function, because for a function, for every x, there had to be a unique y, such that f of x is y. And here I have 3 values. So in calculus, at least for now, we'll restrict ourselves to curves that are graphs of functions. We'll relax that later. So curves like this, for example. What about curves like this? It's not smooth. It's got this corner at the top. That's fine, at least for now, and we'll make restrictions later. We'll start to classify these different curves in different categories. Okay, what about punching a hole in the graph? So for this x, there is no y. So we have to find a y somewhere on that line. What about here? So the graph is nice and smooth, except for at x, where it has a jump in it. And we could choose this value of y, or this value of y, or this value of y. In fact, there are infinitely many choices we can make for y, other than the one that seems natural to us. But only that one gives us a continuous graph. Somehow choosing that value feels more natural. There's something about smooth and continuous curves that we just love. So at any x on that curve, we could punch a hole in that curve and choose any of the infinite choices for y instead. That brings us back to our principle. In calculus, we'll mostly work with these smooth and continuous curves, but in calculus, although there are many more curves that are not smooth than are smooth, although there are many more curves that are not continuous than are continuous, in calculus, for now, we're going to choose good over evil, and we're going to work with smooth and continuous curves. And so next time, we start the journey to figure out what this means and how we can tell.